Okay, so I have a bit of a cold today, so just in case it's something that can be spread, I'll try to keep a distance. So yeah, so let me continue with this part. So the picture that I was describing last time is organized in this way. You're trying to make a model of the interface between syntax and semantics, where on the semantic side, we're trying to keep things as minimal as possible. And then I'll show later today how you can actually add more things on the side of semantics if you want. But the basic property that we're taking on the semantic side is the fact that semantics is some kind of open condition. So meaning is sort of described or modeled in terms of what things combine well with other things, so what things are close to other things, and how you can interpolate between things. And so the model, so you want some kind of space that has this property, some notion of proximity and some notion of interpolation. So for example, something that's like a geodesically convex piece of a Riemannian manifold, or, well, for example, a vector space that's, well, in the simplest case, has all of these properties. And then we want a certain kind of evaluation of, in general, using some probes, or some kind of semantic hypothesis you want to compare with, and you want to say when you evaluate the structures you are doing and the substructures have correlation or anti-correlation with a particular probe that you're using for evaluation. And this concept of agreement or disagreement is also understood that it can go by degrees. So it can be like a 0-1 thing where you have total agreement or total disagreement, or it can be something more gradual where you have some kind of intermediate threshold of agreement or disagreement. And so, as I was saying last time, is that this threshold this notion of threshold is actually modeled by the same kind of Proto-Baxter structure that is used for separating convergent and divergent things in physics, just applied in a semi-ring context. So the examples that I was discussing last time are based on this idea, and I'm gonna. So so we've seen the example that use the Max Planck, the Max Plus semi-ring with the ReLU threshold, or, well, the Boolean semi-ring with the trivial threshold, which is just the identity. So just the case where you have 0-1 for agreement, or a probabilistic semi-ring with a threshold on so when things are sufficiently likely or not so much. And so, as I was saying last time, the same recursive procedure one uses in physics to check over consistency over substructures will identify chains of substructures that have the largest possible agreement with a certain probe. So you can see where agreement and disagreement are located in terms of substructures of a particular structure. So this is pretty much where we were last time. And so, just to make another example, if you take this probabilistic parsing, where your semi-ring gets the interval 0-1, the maximum and the multiplication as your semi-ring operations, and you have these threshold operations as the Roth-Baxter operators of weight -1. You can, if you have a map that represents lexical items into some kind of semantic space, which is some topological or metric geodesically space, then you can inductively extend this map to actual syntactic objects, provided that they have a well-defined head function, and you basically follow the head. So it's again this idea that you think of when you put together two things with a merge, and one of them is the head. Both of these leaves are mapped by this map that you already have to semantic space, and you locate the root of this cherry tree somewhere on the geodesic arc between the two, And you think of it where you locate it in terms of what is the head, so what is the most important part, and how much it is modified by the other in terms of how correlated these two things are. If they're highly correlated, you're modifying only slightly. If they're less correlated, you're modifying it more. So of course, it's a very simplistic, and like oversimplified model, but it sort of shows that you can, have embeddings of structures of, syntactic objects inside a semantic space constructed in this way. And if you do this Birkhoff factorization with respect to this threshold operation on this Viterbi semarin, then what you will get is maximizing. So the maximizers will be chains of nested accessible terms that will carry where all of them carry a large semantic agreement between the various constituent parts. So it sort of shows you where agreement is concentrated. And so in particular, as I was saying, you get an image by this construction. You get a simple-minded way of constructing an image of syntax inside semantics, where your trees are embedded as trees made out of geodesic arcs in your semantic space. Okay, so this kind of says something about this side of the picture that I was describing, and we have already talked about these two sides. So how does one compares these various things? Well, there's some way to actually keep track of all of these data at the same time. Again, this is a simple model, but one can see that there's some interesting geometry that accounts for how you combine this data together. So one thing here, right, is that on this side, you're choosing planar structures on trees. And on this side, you're assigning metric structures on trees because the moment that you embed the tree as geodesic arcs, now the edges of the trees have lengths assigned to them. Whereas here, they're just combinatorial trees. So there are two things that happen in this picture. One is the trees become planar, and one the trees become metric. And these two things can be combined. There's a nice space that parameterizes all of these choices at the same time. So the comparison between different planar structures on the same underlying abstract tree is accounted for by a combinatorial object, which is called the associahedron, which I'll say something more about in a moment. And the metric structure that is coming from the embedding in the semantic space is accounted for by another kind of geometric object that I'll also describe in a moment, which is called the VHD modular space of non-planar binary rooted trees with metric data on the edges. And the thing is that these two objects a priori don't really talk to each other because one of them is just looking at different planar structure on the same abstract tree, and the other is looking at assigning matrix data on an abstract tree. But there's a place where both of them can be combined together with the suitable maps to both of them. And this is another object that is well known in mathematics. It is actually the modular space of curves of genus 0 with marked points, but real curves of genus 0, rather than the usual M0 and bar with complex curves. Okay, so I'm gonna just go through a bunch of these geometric data and sort of fill in the geometry in that pictures that I showed a moment ago. So these are like some of the references for some of the of these geometric data that I'll be talking about. I will post these papers on the web page of the class. I haven't done it yet, but I'll do it. Sure. Okay, so this is what's gonna happen now. I'm gonna revisit this picture, and we're gonna have associahedra on this side. PHV moduli spaces on this side, and their combined picture is going to be moduli spaces on real curves. So the associahedron was originally introduced by Stashev, although I think it was probably also in some other references around the same time, for reasons of use in homotopy theory. And so you have an associahedron Kn for each n of n greater than or equal to 2. It's sort of trivial in the case of n equal to 2. And it's a convex polytope, which is of dimension n minus 2. And so the way you describe it is that the vertices correspond to all the possible balanced parentheses insertions on an ordered string of n symbols. So if, of course, putting balanced parentheses expressions is the same thing as building a binary rooted tree, a planar binary rooted tree with that string as the set of leaves. So these are the vertices. They're labeled by all of these possible choices of parentheses, and you have an edge between two vertices. Whenever the bracketed expressions of the two vertices differ by a single associator, so a single place where you change, where you apply, this operation is not associative, so you replace one bracketing with the other one. And so, for example, in the case where n is equal to 3, well, you have only two ways of bracketing a string of A, B, C. And one of them is this, and one is this other one, and they differ exactly by one of these lack of associativity laws. And so the associahedron K3 is simply a one-dimensional convex polytope that has two vertices and a single edge between them. In the two-dimensional case, one can sort of easily see that by doing the same thing, that you get a pentagon as the corresponding associahedron. The three-dimensional associahedron K5 is a bit more complex to visualize, and this is like the front and the back pictures of the same thing. And again, all of the edges just differ by one of these transformations. So here, right, this is a purely combinatorial object in the sense that you just specifying the vertices and edges, and they just correspond to these assignments. There is no matrix data on the corresponding trees. These are just the different planar structures on a tree with an assigned set of leaves in a fixed order. Right, so you can think of it this way. If I fix the leaves and I order the leaves as a set, then what are all the possible tree structures that are compatible with that keep that ordering in the leaves, the set. So all the different planar trees that have the same order set as the leaves. Okay. But now you can also consider the possibility that the internal edges of the tree have some kind of lengths assigned to them. And so one observation is that an associahedron can always be subdivided into a certain number of cubes of the same dimension as the associahedron, so dimension n minus 2. And that number of cubes is equal to the Catalan number. And the Catalan number is exactly the number of vertices of the associahedron. And so it means that each of the cubes is taken in, like in this case of the associahedron K4, is taken in a single vertex of the associahedron, and that's why there are Cn minus 1 of them. One vertex placed in the middle of the well, n minus two-dimensional top, and then you bisect the faces in this way. So how I'm gonna think of that? Well, I can think of it like this, right? If I go from here to here, I know what is happening. So if I'm at this vertex or at this vertex, I'm introducing one of these, lack of associativity, change in bracketing. But one way to think about how that change in bracketing is happening is to say that, I'm gonna, for example, if I have this planar tree, right? And now I want to bracket these three here, right? So that now, so this is bracketing like this. And if I want to bracket it like this, so that I'm introducing one of these changes, it means that I have to move this vertex to something that's coming out of this branch rather than coming out of this branch. And so one way to do that is to actually shorten this length until I get a tree that is, so I passed at some point through a tree that is not binary anymore, where these two vertices collide. But then I move the vertex off to this other side, and then I see again a tree that is binary, but where I moved one of the leaf on the other side of the next vertex, right? And so I get that wherever I am inside here, for example, I'm looking at if this is the bracketing that's associated to this vertex, I'm looking at trees like this, and where I have two coordinates on this square. The two coordinates on the square are these two lengths. And when I go to one side or the other, one of the two lengths is going to 0. And then I get into the other square where then the two lengths will correspond to the internal edges, the lengths of the internal edges of another tree structure that corresponds to this bracket, and so on. Okay. So this means that, okay, you can think of this as this metric structure that are assigning certain weights that are non-negative real numbers to the internal edges of the tree. Okay, so now let's just look at the other thing that I mentioned, which is the BHV modular space. It's the sense of Biller, Holmes, and Faulkner. And this so far we've been talking about planar trees and bracketing on an ordered string. But now we're looking at trees that are not planar, so they're just abstract binary rooted trees, again with n leaves. And there's again one of these modular spaces for each end. And again, we are assigning weights to the internal edges of the tree. And also, normally one considers a one-point compactification of this modular space, because by itself is, of course, your weights can become arbitrarily large because you can make your edges arbitrarily long. So that's a way to compactify. But so now there's a different picture in terms of the combinatorics, in the sense that if I have n labeled leaves, but now I look at all the abstract, not planar, abstract binary rooted trees with that set of labeled leaves at the bottom, they're going to be 2n minus 3 double factorial such trees. So that's the combinatorics for these objects. And now for each of these different choices of trees, you have a corresponding order of all the possible weight lengths that you can assign to the internal edges, and there are n minus 2 internal edges on a tree with n leaves. So that's the thing. So you're gluing together, and these many, orthants with that parameterize all the possible choices of weights on all the possible trees that have the same set of leaves, of labeled leaves. So for example, if you are in the case with n is equal to 3, then you just have a single parameter, because you really only have one of these edges that you can use to move, the bracketing. The other ones don't move. These remaining edges don't move the bracketing. So the one that does move the bracketing is only this one. So you have like a one-dimensional R plus or negative for each of the three possible choices of abstract tree with the same set of labeled leaves. Now, since they're abstract trees, you can view them as the same tree in this case with three leaves, right? In this case with three leaves, they all have the same tree topology, but with different assignments of the leaves, of the labeled leaves. And again, these are joined at the point where this length goes to 0, which is the point that you use to cross from one branch to the other. And the one-point compactification then is just the one that joins together these three lines at a single point. So the compactified PHV moduli space in for n equal 3 is just this graph. More generally, right, if you look at the case of PHV4, then now you have different possible tree topologies. You have some that are not the same equivalent topology, and again you have the different possible. Now you have two choices of edges that you can vary in length, and that allow you to move from one piece, one part, one chart to another when one of the lengths is going to 0. So this each of the parameterizations is a square because it's just these two coordinates of the internal edges. So in particular, if you don't care so much about the lengths becoming arbitrarily large, I mean because the lengths going to 0 is useful to go through the boundaries between these different cells, but if you don't care so much about the lengths going to infinity, you can kind of normalize these lengths, which means that what matters in terms of the topology is really the link of the origin in this, which you can think of as being the case that's normalized, where the lengths, for example, if you consider that the lengths add up to 1 or something, do some normalization on the lengths, then you get a section that is topologically equivalent to the link of the origin in this modular space. So, for example, in the case of n equal to 3 that we've seen here, obviously the link of the origin is just 3 points. It's very simple. But when n is equal to 4, you have a few of these that combined together, and the link of the origin is this is a graph. Now it's going to be one-dimensional, and it is this Peterson graph. So that kind of captures the non-trivial topology of this modular space of metric trees. Okay, so now you want the relation between these two, right? On the one side, we have the associahedra, where we have also introduced the lengths of by this decomposition into cubes of the associahedra. Then on the other side, you have these BHV modular spaces, which are for the non-planar trees with the metric structure. And so these two things have to talk to each other. And so you want some space that specializes to both of them. So as I mentioned, the one geometric object that does account for both of the spaces at the same time is the modular space of real curves. In fact, the orientation double cover of the modular space of real curves. So of course, because we are with real geometry, we have to worry about the orientability of spaces. And it's the first couple of ends, this modular space is orientable, but then it starts being non-orientable. So you consider its orientation double cover as the actual thing that you want to work with. And this is because the other two things that we've seen are orientable. And so the way to make the connection between these is to think of So you have this set of ordered, on the side of the associaedra, you have this set of ordered leaves of the trees. And you can realize this set of ordered trees as a set of points inside the real line, because, well, there's some ordering, right? So any set of points that's ordered in the way that you want it ordering to be. But now, okay, that's just some choice of points in the real line that have the same ordering. But now you want to also encode the information about the lengths of the edges, of the internal edges. And so that now is going to specify how distant these points are from each other. And you can do that by looking at the path between these points and the root. So, for example, if I want to do say I want to decide how distant from each other I put the points in the real line that corresponds to these two leaves, I can look at the path that goes from this cherry of these two leaves to the root. And I have two edges to account for, and I take the total length of this path. And okay, one can just put it in this exponential form, but basically the information is just the length of this path. And so that's right. Again, you can make this the path, the total path. Make this total length, the path of the path from the root to this total structure that you have, and so on. Okay, so you have basically in this way, you have encoded not just the ordered set of the leaves, but you have encoded the tree structure, because the lengths are seen not just the distances between this point, but actually the distances in the tree between from the leaf to the substructures. So you have encoded the tree structure in this as well. And so now you have a configuration of points on the line. So this moduli space is exactly taking care of parameterizing configurations of points on the line of P1 and it's compactified. So this bar M0 plus 1 bar means that it's compactified, and the boundary strata are where some of the points are allowed to collide, which is exactly the kind of because the distances between these points are the lengths that I'm putting on the internal edges of the tree. So making two points collide means exactly making one of these lengths go to 0. So these boundaries in the M0 and plus 1 bar are the same as this boundary between the cells that we're seeing in the case of the BHV and the associaedra. Okay, so the also another fact that's well known for the moduli space of curves, both in the real and the complex setting, that you can always fix 3 points by an automorphism of P1. So you can always fix 3 of these points to be 0, 1, and infinity, which means that the dimension that you have left are only the remaining points. So that's why you get this the one that is of the correct dimension to match the associaedra and the BHV moduli space is the M0 n plus 1 bar, because the remaining 3, once you fix 0, 1, and infinity, there's an n minus 2 of possible variable dimensions, and so that's of dimension n minus 2, like the associaedra. Okay, so now the more precise relation between the orientation double cover of the moduli space of real curves, the compactified moduli space of real curves of genus 0, and the associaedra, is that you can decompose the orientation double cover of the M0 n plus 1 in terms of a union of associaedra. And there are n factorial associaedra glued together. And so what is going on here is sort of clear, right? Because every associaedron is associated to, so it's describing a situation where you fix an ordered set of leaves, and then you look at all the bracketing for that ordered set of leaves. But And now, if you're looking at all the possible configuration of points on the line, you're supposed to also be allowed to permute the points. And the n factorial associaedra are exactly the ones that are obtained by permuting in all possible ways the string of leaves, the order string of leaves. And so that's the reason why you expect that there should be the composition of this kind. And the actual gluing maps are a bit delicate to describe. I will post the paper of Tevados and Morava on the webpage that has the details of how you construct this gluing. But one can see it, for example, in the case of K4. Okay? So each associated K4 is a pentagon. So and the way that they assemble into the M05 bar is something like this, where you glue together all these pentagons, and it has two hexagonal holes. And then the orientation double cover is two copies of this picture glued together. And so it's actually has it's a surface, a real surface of genus 2. And it has and the actual way in which these things are assembled together, it's so there are a total of 24 associaedra that are glued together, and the way they're glued together, they form this great dodecahedron picture. I mean, this is sort of when you embed it in R3, you have to kind of cut through itself, so it's immersed. So some of these places like continue, but the picture is this. And of course, in higher dimension is some more complicated space, which is cannot visualize in this way, but it's still obtained in the same way, like gluing together n factorial associaedra Kn. And so now the thing is that you have both the relation to the associaedra. The associaedra are the building blocks for this modular space of curves that you glue together in this way. But you also have a projection map to the BHD modular space. The projection map comes on this, the way that the projection map works can be seen in terms of this combinatorial identity of binomial coefficients and powers that has so on this side, it has n factorial, and it has a Catalan number. This Catalan number is the number of cubes in your associaedron. Okay, so this is on the side of the way that the associaedra tile up the modular space of curve. You have n factorial associaedron, and each associaedron has Cn minus 1 cubes. This is what is happening down here. So this is the number of cells that you have down there, because it's the number of possible different trees, non-planar trees, with a given assigned labeled set of leaves. And this is the multiplicity of the fibers. So these are themselves cubes, because they are these orthants, and you can normalize them to be cubes. And so the thing is that you map these cubes to these cubes, but you do it in such a way that this is the multiplicity of the map. And what that multiplicity corresponds to is this origami folding map. That, for example, in this case where the pieces are two-dimensional, you have four squares at a time. So this is the multiplicity of your fiber. Well, 8 because it's the orientation double cover. But in each sheet of the orientation double cover, you have 4 of these cubes, these squares in this case, and the projection map is just folding them together like this. Okay, so this is generally the way that this map works. It's just folding together all these cubes into the corresponding cells of the BHD modular space. Okay, so where are we when we are parameterizing things like this, right? So suppose that I pick a sentence, so I have an ordering. This is after my externalization, so my actually ordered, in the way that we do encounter them in spoken language and written language. And this is and then there's a certain parsing for the syntactic structure that corresponds to this sentence. And this parsing is determining a certain vertex in the corresponding associated. And so and in particular, this is happening in one of the 24 associaedra that corresponds to all the possible trees or all the possible permutations of this set of things. And so this means that, in a sense, what we described as this section is a part of the externalization map that is choosing the planar embeddings, is exactly choosing one of these points in this associaedra, one of these vertices in this associaedra, as a section of this map to the non-planar trees. So indeed, the underlying syntactic object prior to externalization is just a non-planar tree with the same leaves. And this is in particular the corresponding parsing structure that fixes the tree topology is one of, in this case, 15 possible topologies with the same set of labeled leaves. And these 15 possibilities are the edges of this link of the origin in the BHV4 modular space. So at the level of pre-externalization, the syntactic object, we are choosing one of the edges in this structure. So on the other side, we are choosing one of the vertices of the association. On this side, we are choosing one of the edges of this link. And now, I mean, on this side, we are also keeping track of our embedding of the syntactic structure inside the semantic space. So assuming that you have a way to measure the relatedness of the various elements in the various syntactic lexical items at the leaves of your structure, you can, for example, in this case, right, you have two coordinates to evaluate, which are the relative proximity of these two pairs of terms. Okay. So that is going to give you two coordinates. This is like a measure between 0 and 1. So it's like the likelihood of being more related or less related. So you get two coordinates in the unit square. And that is the cell of the BHV4 that goes through of the BHV4 compactified. So one of the points is at the compactification infinity that goes through this particular edge of the link at the origin that you have selected. Okay. So for each of this link, you have a corresponding cell, which we should represent as a square. And these are all glued together according to the link. And you are just picking a point on somewhere on this particular cell. Okay, so this is a way of kind of representing geometrically this map of the syntactic objects to the semantic space, compatibly with the externalization. So everything is, if you want to think of everything as being happening at once, which, I mean, in a sense is not so relevant for when you're producing language, whether these things are happening at once or not, they are just happening. In a sense, externalization is the last thing that happens when you're actually, so you can think of semantic parsing as something that goes on earlier just in terms of it. But when you are at the parsing end, the receiving end of language, then everything comes combined together. So you are somewhere in here and you're kind of projecting down to here to get your position in semantic space. So this means in particular that we know that we have this choice of planar structures is language dependent. It depends on the word order parameters of a particular language. So different languages when it comes to externalization will correspond to different sections of this projection from this modular space of curves to this BHV compactified BHV modular space. And the way to compare them is, you can, since they are sections of the same covering map, you can compare them in terms of the action of this group of covering transformation of this covering space. And so in particular, like there are these proposals of like linearization algorithms, like I mentioned the one, Keynes CA, where you follow ahead of the tree to make the choice of planar structure. And again, you can compare that with the actual planarizations that are coming from the syntactic parameters of a particular language, again, in terms of the group of covering transformations of this space. So this just gives like another possible point of view on how one can do comparative syntax in terms of the comparing different sections of this. At least, of course, this only takes care of the part of syntactic parameters that have to do with word order, not with other ones, but at least for comparative word order structures, you can think of them this way. Okay, so this is, yeah. The next thing that I want to talk about so as I said, so everything that I said so far is using a very minimalistic view of how you model semantics. And part of the picture, part of the idea in all this was exactly to like remain as agnostic as possible about what semantics is. So you just assume that the minimal thing they want to have is some notion of proximity, some notion of interpolation. And okay, we get out of that you can have some kind of functioning, parsing algorithms for parsing semantic consistency of syntactic objects, regardless of which specific model of more detailed model of semantics you want to consider. Of course, there are if you look at how people have been thinking about semantics in the context of generative linguistics over time, there's a different point of view, which is that you actually do want more structure on the side of semantics. And in particular, there are two kind of ideas behind this point of view. One is that, like in the same way in which you compose syntactic objects by merge on the purely computational side of syntax, you want to be able to compose or combine concepts on the side of semantics. And that somehow the merge operation that you have on syntax should reflect or map to some other compositional structure that lives entirely on the side of semantics and that combines concepts in the same way that you combine structures in syntax. And that's one point of view. And the other point of view is that the syntax, we presented it as a kind of computational structure. It's not the only computational structure that exists in our brain. There are many other computational structures, but so, for example, manifestly, we can not just produce language, produce elaborate syntactic language that is organized in elaborate syntactic structures, but we can also do logical operations. And so, which are part of, for example, what we do when we do mathematics. Our brain our brain can do mathematics, just do language. I mean, there's some overlap between these things, but they're not the same thing. So one of the other ideas is that some form of logic should also be part of the package of semantics. And in particular, when you map syntax to semantics, one of the things that you're doing is you're checking for logical consistency with respect to some form of logic. Okay, so I'm gonna just say a few things about how people have been thinking about this and how they relate to this more simplified point of view that I discussed so far. So the first thing that I mentioned, this idea that there is something that's similar to merge that exists on the side of semantics, is called Piotrowski compositional semantics. And it's based exactly on this idea that there is like a parallel structure that is the merge operations in syntax and a kind of combined operations in semantics that combines concepts in the same way that merge combines syntactic objects. And the way that Piotrowski describes such an operation is as the composition of two things. So it calls it combine, and it's described as the composition of a labeling operation applied after a concatenation operation. So the formulation that we gave for this was actually developed in the context of the older form of minimalism for syntax. So, trees are assumed to be planar to begin with, and merge was supposed to like apply to planar trees after some feature checking and domain matching and so on. And but in particular, this was designed to apply to the case of planar trees, not to the case of non-planar trees. And I'm going to show in a moment where the issue comes in, where you look at it from the point of view of the new model of minimalism. And the main point, right, the main reason why there's clearly going to be some issue is that in this original formulation, the first of these two operations, the concatenation, was defined as concatenation of strings. So we were just looking at the strings that occur as the leaves of your planar trees, and you just compose strings. This is in a sense interesting because there's currently people try to build some kind of viable mathematical models of what large language models are actually computing, and some of the most reliable or most promising models that proposed are based on this concatenation of strings and some algebraic structure around this concatenation of strings, where you have data probabilities together with this algebraic structure. I'll hopefully come back to that later. But this is sort of, in a sense, a similar idea that was happening in this formulation of Piotrowski. So this concatenation operation on strings. So you take your finite set of lexical items and syntactic features, and you form ordered strings of arbitrary length in this set. And the concatenation is just simply taking two strings and putting the first one after the second, if you read it from right to left. And so in particular, you want to think of this as being applied to the ordered set of leaves of a planar binary rooted trees when you combine two planar binary rooted trees by the non-commutative merge operation. So the idea is that if you have a merge, so you have like the case of the syntactic objects, where you have the free non-associative commutative magma on the set of lexical items and syntactic features. You have also a non-commutative version where you take the free non-associative and non-commutative magma on the same set. And these are the label, the planar, all the possible planar binary rooted trees with labels in associated. And as we've discussed before, there is a canonical morphism of magmas, which is the projection that forgets the planar structure. And if you start with an abstract tree, there's no magma morphism that goes the other way. But like we've been discussing for externalization, you can choose a section of this projection that is not a morphism of magmas anymore, and that just chooses a planar, a point in the fiber of this projection, so a planar structure for it. And so this, so particularly you have a map from this magma of this non-associative, non-commutative magma to the strings in the set of lexical item and syntactic features, which assigns to planar tree the order set of its leaves. And this is a morphism of magmas, that the concatenation one is also a magma. And except that this concatenation operation is associative. The magma of the planar binary rooted trees is not associative because the structural tree is not associative, but the concatenation of strings is associative. So this map is actually killing the associators. Right? So it's just the projection, it's the natural projection, there is a morphism magma that kills the associator. So we have the canonical map that kills the commutator and the canonical map that kills the associators. Okay. So this, however, means that one issue that you have is that if you're now seeing things from the point of view of the new model of minimalism, where syntactic structures are generated as non-planar trees, and then they are planarized by some kind of choice of a section, which, let's just say, some linearization algorithm. It could be your language-dependent externalization. It could be built using a head function. So anyway, some choice of a section, right? And the problem is that now, since you're starting with the commutative magma of the non-planar trees, when you try to apply the same L map, you end up with the problem, the fact that you're going to run into obstructions to having a consistent definition of this concatenation on the image of a linearization algorithm, meaning that if you planarize the tree first and then you apply this, or you merge two trees with a free symmetric merge, then you linearize it by your algorithm, and then you just extract the string of the leaves, or you first linearize each of the two trees and apply the corresponding strings and look at the corresponding strings and you concatenate them, you don't get the same thing. Okay. So in fact, there's a good way to characterize in terms of this geometry that I just described of the associahedra and the moduli spaces, exactly where the possibility of doing this concatenation on strings fails if you are using the free symmetric merge and a linearization of the. So let's see how to characterize this. So we have these two projections, right? The one that kills the commutators and the one that kills the associator. So the projection pi, which is the one that kills the commutator, is the one that goes from the moduli space of curve to the BHD moduli space. And it has fibers that have the 2 to the n-1 different choices of planar structure of a given tree, of a given abstract tree. And if now you merge two trees and then you linearize, so you use a section to choose a planar structure, or you first choose a section and then you merge with the non-commutative merge, these are going to have the same order set of leaves, meaning that concatenation is well behaved, if and only if they differ by a change of bracketing. So if and only if they are different vertices on the same associaedron inside this modular space of curves. Because being vertices on the same associaedron means exactly that the corresponding string, order string of leaves is the same, although the tree structures need not be the same. So these two S3s will disagree in general, but no, I'm saying that the concatenation is the operation on the strings of leaves is still well behaved, provided that they differ by being at different vertices of the same association. Okay, so and we know that there are Cn minus 1 such vertices, right? Because the associatron has a number of vertices that is equal to the Catalan number. And so now we look again at this combinatorial identity that I discussed a moment ago. So you have these Catalan numbers, which are all the possible bracketing on a fixed order set. So the number of planar trees, but with the same order set of leaves. You have the double factorial that counts the number of different abstract non-planar binarily rooted trees with n labeled leaves. And this is the number of abstract trees with the same non-ordered set of leaves. And then you have this multiplicity 2 to the n minus 1, which is the number of possible planar structure on each tree. And the n factorial on the other side is the number of possible ordering of the non-ordered sets of n leaves. Okay. So this again is all the ingredient, the counting ingredients that you have in this picture. And so now let's say that I have a planar binary rooted trees, which I have obtained by a choice of section that planarizes trees. And if I act, so I can act on it with the symmetric group, and which is acting on the leaves by permuting this ordered set of leaves. And so it's moving between the various associaedra by doing that. And so this tree that I start with, theta is lying at the vertex of one of the associaedra, and the orbit is touching a vertex for each of the other, a single vertex for each of the other associaedra. Exactly, n factorial. So you can in particular look at a group of transformations that, so we have these other, so this is all happening in this counting here, right? But so in terms of this counting here is to the n minus 1, we can look at the group. So if I have a planar tree, I can look at the transformations that at each of the vertices flips the two left and right sides below the vertex. And if I take the groups that are generated by these transformations, this is the one that generates all the other possible planar structure of the same non-planar tree from a given one. And so that's the one that takes care of these 2 to the n minus 1 multiplicity. And this group has a normal subgroup, which is the one that preserves a certain, so for each planar chosen planar tree, it has a normal subgroup that's the transformation that fits that particular tree. And so that if you want to count the orbit under the action of this group, it's just going to be the overall group divided by the things that don't change the particular tree that I'm looking at. And in particular, the relation between these two sides of the identity that I've written there can be rewritten in this form where I'm summing up these orbits, the length of these orbits. If I sum the length of this orbit, I just get exactly the terms that are in this relation, in the same combination. Okay, so I mean the corresponding picture is something like this. On this side, you have the BHV modular space. On this side, you have the associahedra that are, so here each associahedron is just an edge, but they are all glued together by these group actions, and the projection map gives me the different branches of the BHD modular space glued together at the origin. Okay, so if I'm trying to linearize tree by some prescription, maybe coming from syntactic parameters, from heads, from whatever, so using a section. And if I look at, so I'm trying to compare the merge and linearization with linearization and merge after. And these are going to be in the same fiber over the underlying non-planar tree, because that's obviously the same. So there is some transformation in this group that will change one planar structure to the other. And so the incompatibility between, where the incompatibility between a particular linearization algorithm and the merge, this asymmetric merge, will occur is all pairs for which this transformation is not in this trivial subgroup. So it's like the points in those orbits that I was discussing. So it's kind of, again, a group theoretic description in terms of certain covering maps, certain covering transformations, covering maps of how how the failure of this concatenation operation being well defined on the free symmetric merge occurs. Okay, so there is this issue that this idea of Petrosky of having this combined concatenate operation on that reflects the merge is running into this issue. So what you can do is reformulate it in a way that it uses the free symmetric merge rather than the strings. And so you can come up with the same idea where this combined operation described by Petrosky is a concatenation that now is commutative, is no longer a concatenation of strings, is the actual merge of trees. And the labeling that keeps track of the head. So we are assuming that these trees are parsable by a head function. And so, but this means that if you want this to be the computational structure on the side of semantics, you want your semantic space to essentially have exactly a copy of the merge operation that you have in syntax, because this is exactly the same operation. In the previous formulation, you can say that it's a different one that acts on strings, but here, if you want compatibility, it actually has to be on the nodes the same merge that you already have on the side of syntax. So in a sense, this okay, why do you need two copies of the same thing? You already have it on the side of syntax. And so this, the bottom line here is that there's no need to, enrich your semantic space itself by the same kind of magma structure or algebra structure that we have on the side of semantics, and ask for a map from syntax to semantics that is a morphism of all of these structures. You don't have to do that, because you can just have this kind of computational structure on the side of syntax, and just use the embedding of your syntactic structure into semantic space without the semantic space itself in computation. You can define your combined operation just by computing merge on the side of syntax and then mapping it to semantic space by whatever your embedding of syntax into semantics is. So there's one question that I had about this is the fact that so far I've been talking about embedding syntactic trees into semantic spaces by these geodesic arcs. But in terms of if you want to do something that's more like logical operations and so on the semantic side, you sometimes want to have thidempotent structures. So when merging something with itself is is itself. It's not, I mean, if you think in terms of trees, of course, if you have a tree with the same label alpha, Charlie tree, it's not the same thing as a leaf or biopsy. There are no idempotents in the magma syntactic objects, but sometimes you might want to have the possibility of having idempotence in the image under this map in your semantic space. But of course, this image, it doesn't have necessarily to be constructed in the way I said through geodesic arcs between the points of the, where you map the lexical items. You could allow for the possibilities that, for example, when I said, okay, the way I described it before is I have alpha and beta. I know where they map to semantic space. I take the geodesic arc between S of alpha and S of beta in the semantic space. And then I place the intermediate point, which is the root of the tree, somewhere in between, depending on how the ratio of similarity or relatedness between alpha and beta is. And I'm usually assuming that this is some number that is strictly between 0 and 1, because these are like two different points in semantic space. So they could be highly correlated, but they would not be exactly matching. But you can also allow for the possibility that this measure of relatedness could include the value 0 and 1. And if you do that, then this position where you place the intermediate point on the geodesic arc between S of alpha and S of beta will be exactly at one of the ends. And so that would give you the idempotent structures that you can also have in this case. So it just generalizes slightly the second that we have discussed before. And also, like for example, the way that one of the examples for which this Petrovsky semantics was illustrated were the kind of sentences that are adjuncts to verbs, right? It's where you want to do this kind of like logical parsing. For example, if I say John ate a sandwich in the basement and John ate a sandwich at noon, these don't imply that John ate a sandwich in the basement at noon. And of course, this is a matter of intersections and unions of open sets, right? So the way you can think is that, if we stick to the idea that your semantic space is some kind of metric space that has a proximity relation and the notion of open balls around points, you can say that if you try to take the geodesic arc, so I'm just drawing a straight line here between these points and locate the intermediate vertices, you can see that the respective balls would overlap, but not so exactly reflecting the fact that the logic is parsed correctly. So this actually says one thing, which I'll say something about a bit later. But if one wants to argue like where is the logic coming from, right? So if I'm assuming the minimal assumption about semantic space that is just some kind of topological space, where is the logic coming from? Well, I mean, there's different forms of logic. And so there's Boolean algebras and there's Heyting algebras, which are the kind of intuitionistic logic. And these ones, which there's various kind of arguments about whether this is really the kind of logic that our brain naturally uses or not. I mean, there's like some discussions on that. But one thing that's nice is that these kind of logical algebras, these Heyting algebras that correspond to intuitionistic logic, they are completely characterized by, so they are the logic of the set of open sets in a topological space. So this means that if you do have a topological space, like in this picture, right? If you do have a topological space, you do have an associated logic that comes with that topological space, and you don't have to require it as an additional structure. It is already there. It's already, so assuming that semantics is kind of a topological structure is not depriving it of the possibility of also being a logic. Okay. So there's one more case of semantic models that I want to discuss, and that is being used quite a lot in the context of generative linguistics. This is called the Heim-Kratzer semantics, and it's based on an inductive construction of types. And I'm going to say in a moment a bit more about that. So so by the way, this is also kind of very, very naturally connected to this idea of intuitionistic logic, and which I'm not going to discuss here, but what Lindelof type theory is also based on intuitionistic logic. And but what I will discuss here is that this setting also has a topological version. So the way that it's normally formulated is that you have a certain class of types, and each of these types has an associated set, which are all the possible denominations of that type. For example, there is E is like a type of individuals, and E is the set of things that are individuals. And there is a type T, which is the type of truth values. And this is just a set 0, 1, because you only have two truth values. It's either true or false. And then, so this is just the basic things that you assume as a given. It's like you're starting your 0 step of the inductive construction. And then once you have more than one type, you can define types of functions. So you can define a type that goes from E to T, which is just, it's things that are of that type are functions from the set of individuals to truth values. Okay. So what does it mean that you have a function from a set of individuals to truth value is something that checks whether that. So what is a truth value? If I have in my set of individuals, I have a banana, its associated value is true if it is a banana. It's false if it isn't. Right? So these are the function that checks if something is a banana. I have the function that checks something else. So these are what these functions to truth values are. And once you do this, then you can define inductively a large set of types, where whenever you have two types that are already defined, you just define the type of functions between the corresponding sets of denominations. So in this case, in this Heim-Kratzer semantics model, the semantic space is the union of all these sets, or that are the denominations of all these different types. So it's a very large set of functions. That is what the semantic space is like. Okay, so what do you do with this semantic space? So there is a notion of interpretability in semantics. This says that, well, let's phrase it in our setting. So let's assume that you do have a map from your set of lexical items and syntactic features to the semantic space that is given. This is sort of what is learned as in the previous phase. And you want to extend it now to a function to syntactic objects which have a well-defined head function to the same semantic space, which means that if I give you a tree, a non-planar binary rooted tree that has a well-defined head function, it will have to map to some function between types, some functions between some types. Okay. So the prescription of how you do this mapping to types works in the following way. So it's inductive over merge. So if I can always describe a tree as a merge of two other binary trees. So if I have already defined how to construct it for the smaller trees, I'm going to say how I want to construct the assignment to types, to denominations of types for the merge tree. So I assume that I have a tree that's obtained as merge of the free symmetric merge of two other non-planar binary rooted tree, and I assume that I have the values in the, so this is just a notation that they use for a function between time, for an object in this semantic space of types of functions. And so I assume that I have this stuff. So, well, now the condition for this merge to be interpretable is that, well, this is going to be a function between two types. So let's say it's going to be a function from d sigma to d tau. And the other has to be something to which I can apply this function. Well, this tree is non-planar, so it can be either way. Like it can be one of them is a function, the other is an argument for this function, so that I can compose them. And the composite is what I assign to the entire structure. So this is, this type as a way of building in a form of compositionality in semantics, where you build over substructures, because the interpretability is the fact that these substructures fit together consistently by these properties of being a function that you can evaluate on a domain. Okay, and if this doesn't happen, right? If neither of the semantic values of the two subtrees that are merged is a function that can take the other as an input, then simply your tree is not parsable in the Kratzer sense. And so one can see by the way that if you do this and you see that something is not interpretable, the non-interpretability can depend on various things, in the sense that the non-interpretability can be due to, for example, a mismatch between function and input at any one of the internal vertices of your tree. Every vertex is a matching of function and argument. So it can result in non-interpretability, due to whatever can happen in any of the internal vertices. And of course, this is again one of these cases where you want to break up your structure into substructures and check the interpretability separately over the various pieces to actually have a way of detecting exactly where the non-interpretability is coming from, where the trouble is located. So one way to do that, right, is, for example, to build a character with Boolean values, where, well, here again, it means that we use the Boolean semiring. Well, on the Boolean semiring, the only Rothe-Baxter structure is trivial, it is the identity. And we can define a character of the Hopf algebra workspaces just by saying that it's 1 if T is interpretable and is 0 if it's not. And it's multiplicative over Forest. And when you take the Bogoliubov preparation with respect to the identity Rothe-Baxter operator, then what the maximizers are in the Bogoliubov preparation, they are exactly those chains of accessible terms where all the substructures and the respective quotient structure are all interpretable. And so it's exactly a way to locate where are the parts of your structure that are interpretable, even though the entire thing might not be interpretable. So this is similar to that. This is the reason why I wanted to discuss this case of this proposal for using the Birkhoff factorizations and the Hopf algebra and Birkhoff factorization formalism of physics in the context of the theory of computation that Manin did, is because it's a similar picture. So you can have, unlike what happens with physics, you can have both the situation. So I mean, yeah, you can have these situations where you have very large chains that are interpretable, but the entire structure is not interpretable. Okay, So yeah, so I think I'm almost done. So I'll have to finish this briefly next time. But the one thing that I want to say is that up to here, this construction of types is purely set theoretic. So when you say that the type from sigma to tau is functions from the set of denominations of sigma to the set of denominations of tau, this is a purely set theoretic functions. And this is satisfactory up to a point because it's like saying, oh, I'm checking if something is a table, no, is it true or false? But I mean, if my table is no, missing a leg, is it still a table? So I mean, concepts are kind of an open condition. They should be an open condition. There's some way to modify concepts so that they're not just 0, 1 truth values. So one way to try to do that is to try to introduce some topology on this space of functions, so that you can say when certain kind of, for example, when certain kinds of truth value evaluations are actually pretty close to each other, you can trade one for the other without changing much your semantic interpretation. And so this you can do. So there are two ways in which you can do this. One is by keeping the truth values exact truth values, 0 and 1, but allowing your functions to be varying in a topological space with some kind of continuity. So that you can say two truth value evaluations are close to each other or not, but that's going to depend on the domain. The range is just the interval 0. It's just the two values 0 and 1, the Boolean summary. The other possibility is that you make your truth values themselves being more nuanced than just being 0 and 1. So you can make your truth values being not valued in the Boolean submarine, but valued in the Viterbi submarine that has the full interval 0, 1. So this means that when you evaluate one of these functions, right, instead of having a function 2, 0, 1 from a certain set of denomination, you would have a function to the interval 0, 1. This is also called the fuzzy set structure on this set. And so you can do either one or the other. The thing is that, of course, you're trying to put topologies now on spaces of functions. And so this becomes a kind of question of point set topology. What is the best way of doing that? So what is the best way of doing that, right? Of topologizing spaces of functions? And it turns out that so I'm gonna discuss, finish briefly discussing this next time. But it turns out that if you do the fuzzy set version, then the topology of the spaces is much nicer in a sense. But either way, either with keeping truth values sharp or by doing the fuzzy version, it's still true that you cannot guarantee that these topological spaces that you built on the inductive types are particularly nice topological spaces. So you can assume that you start with as nice as you want a space for the initial type of individuals, say, a geodesically convex Riemannian manifold that is compact, so metric compact, all the properties that you want to have. But when you keep trying to topologize spaces of functions here, you will, so some of them will maintain at least the metrizability, and but some of them lose the compactness, and some of them lose both the metrizability and the compactness. So when you put all of these together in a single semantic space that are all of these function spaces, this becomes not a nice topological space. And there's simply no way to make this a nice topological space. But it's okay. I mean, you can do things with topological spaces that are not nice, but you have to take into account that this is the price that you have to pay if you want to use this kind of model of semantics by allowing some kind of topological structure. Okay, I'll explain this more carefully next time.